Hi class, I hope you're all doing well. Welcome to Friday. We are rapidly approaching the end of the quarter. So today we're going to finish up our discussion of exoplanets, and that will set the stage for the last phase of the class, where we're going to talk about something we've all been waiting for, which is the search for extraterrestrial intelligence in the universe. So we'll talk about that for the last week and a half of class. But today we're going to taper off and finish our discussion of exoplanets, and then we'll move on to the last two chapters of the book. Okay, so to start with, in the image behind me here is an example of very typical exoplanet that we find in the catalog these days. These are Jupiter-sized worlds. And in particular, what's unique about them is we find them very close to their parent star. And so we'll talk a little bit about that here in this first half of lecture today. But I wanted to show you this image. This is something we kind of mentioned in passing during our lectures up to now, but we didn't talk in great extent because we don't do a lot of it yet in terms of our observations. But you'll notice here in this image that the rim of the planet is very bright. And the idea is there that the light from the star passes through the planet's atmosphere around the edges as the planet goes across the star during the transit. In particular, at the times where it first moves onto the star, it goes across the star, and then the times it moves off the star, where kind of part of the planet is illuminated and part of it is not. Those are times where it's very easy for us to look at the light from the star from the planet, the light from the star and the light coming through the planet's atmosphere. And the point in that is that it allows us to measure spectroscopically the content of the atmosphere. And so while that's helpful for figuring out what's in the atmosphere, it's also one of the methods by which we hope we might be able to search for life, looking for what are called biosignatures, looking for relative concentrations and abundances of gases that you and I, on Earth at least, associate with life processes, things like carbon dioxide. Okay, so that's why I picked this image today, but it's also relevant to the topic we're going to talk about this half of the lecture, which is about the architecture of planetary solar systems. Okay, so let me go ahead and start some slides. So at this stage of the game, and by stage of the game, I guess I mean at this point in our observational history, we know of many, many planetary systems. As we discussed last time, there are some 4,000-ish planets known. There are some 3,000-ish individual planetary systems. And so what that allows us to do is to take some cherished knowledge we have, some ideas that we've always had about the way solar systems set themselves up, basically the way our own solar system is set up, and then compare it to all the solar systems that we're starting to discover around other stars in the galaxy. So I'll remind you about the architecture of our solar system. We'll talk about some of the earliest planetary discoveries that we made and what the implications that suggested to us about the architecture of solar systems. And then we'll talk about the plethora of systems that we do know. And the too long didn't read version of this half of the lecture is we're going to get to the end, and really what we need better data than we have. Okay, and we'll talk about that as we get towards the end of this part of the lecture. So the diversity of planets, as we've been discussing, is enormous. We see all kinds of planets ranging from many times the size of Jupiter down to things that were slowly reaching the sub-size of Earth. Not quite much lower than that yet, but as our technology, particularly with regard to transits, gets better, we're certainly going to start to discover smaller and smaller worlds. But the diversity of planets is only part of the story about whether or not we can find planets where life might exist in the universe. It's the combination of the properties of the planet itself and where it is in the system around its star that we have to think about. And so when we look at our own solar system, you'll remember that it naturally divides itself up into these three zones that we call the terrestrial zone, where the worlds are small and rocky, like Mercury, Venus, Earth, and Mars. The so-called Jovian zone, where the worlds are very large and gaseous, But even if those worlds aren't necessarily conducive to life, they certainly always have interesting moons, and many of the moons in the Jovian sector of the solar system might be potentially habitable. And then there's this third zone, which is where the icy Kuiper Belt style worlds are. And Pluto and Charon, as well as the Kuiper Belt and well beyond into the Oort cloud, is where those icy worlds are, the leftover detritus from the formation of our solar system. So before we started discovering planets, we would often try and simulate the creation of planetary systems. Now, part of that exercise on a computer was to try and understand how our solar system formed. And we would tinker with the physics, and we would tinker with the inputs, and tinker with the original mass in the solar nebula, they'd tinker with how fast it's spinning, all of those things, trying to understand what the conditions in the early solar system were that would give us this style of solar system. And if you go back to old astronomy textbooks, before we started discovering planets, okay, so textbooks from the 1980s and the early 1990s, what you saw is that we could indeed successfully simulate solar systems. And many of those solar systems looked not unlike this old one, where you had an inner small planet zone, a kind of in the middle, as we know from our early map of the solar system, the bulk of the solar system in terms of space. But the middle group of planets are the so-called large Jovian planets, and then an icy zone out in the outer rim. So once we started looking for planets, this was the sort of thing that we were expecting we might find. Okay, but you can imagine posing the search for planets in terms of a question. That's often a good way to think about doing scientific experiments, because it reminds you constantly of what it is you're trying to do. And so one might pose the question in the search for exoplanets as being, are the planets around the sun typical? Is the structure of the planets around the sun, in terms of their order and their spacing, what we call the architecture, is the architecture of the sun's planetary system typical or not? Okay, so bearing those two questions in mind, you can start collecting data about exoplanets and then ultimately come to some conclusion about that. And we'll talk about that before we get to the end of this piece of the lecture. So the very first planet discovered, the very first exoplanets, were around the pulsar 1257 plus 12. It's about 2,300 light years away in the constellation Virgo. So if you go out at night right now, not from Chicago, you probably can't see this, but if you're out where it's a little bit dark and you can see all the stars in Virgo, which right when it gets dark is due south, it's right there off the arm of Virgo is the location of the pulsar. You can't see it with your naked eye, but that's where it is in the sky. So the very first planets we ever discovered were around this pulsar. And the reason we were able to discover them is because the pulsar is not an ordinary star. It's the skeleton of a dead star that forms after a star explodes at the end of its life. Okay, and we'll talk about that a little bit in the second half of lecture today. But in that explosion that destroyed the parent star, it almost certainly destroyed the planets. And so our current belief is these planets that we've discovered around this pulsar are not the original planets that lived around the original star before it exploded, but are actually new planets that formed from the rubble of the old planets that was left over after the star exploded. So gravity regrouped all of this material together and gathered them into these new planets that we see here. Now, the reason we're able to detect them, these were detected by the radial velocity method. The reason we were able to detect them is because the pulsar is a spinning skeleton that has a flashlight stuck on one side of it. And so as it spins, sometimes that flashlight flashes across your line of sight, and then it spins away from you, and then it flashes across your line of sight, and then it spins away from you and across your line of sight and across your line of sight. So you get this pulse of radio light over and over and over again. Very steady, very evenly spaced. Pulsars are excellent astrophysical clocks, okay? So if there's a planet around the pulsar, tugging on the pulsar, it affects the very precise spacing of those pulses that we get from the pulsar. And so that's why we were able to detect these planets well before we detected planets around any other star. Okay, so this was unusual. A dead star is certainly not a star like the sun. These planets almost certainly are not the original planets, and so this isn't what we were really after, right? If we say our goal is to find planets to compare to the planets of the sun and find planetary systems to compare to the architecture of the family of the sun, then this doesn't really fit the bill. But it's a necessary step in the endeavor to look for exoplanets. We had to find the first one somewhere, and as it turns out, this pulsar system was particularly good for looking for planets in because we had the technological capability of measuring this system before any other system. Okay? So, when were the first planets around a sun-like star discovered? Well, it wasn't too long after this discovery. So we've mentioned this star before. So this is the star 51 Pegasi. So it's in the constellation Pegasus. So if you look at Pegasus in the sky, it has a great big giant square called the Great Square of Pegasus, as you see in this figure on the right here. So that's called the Great Square of Pegasus, is like the body of Pegasus. And just to the right, to the west of the Great Square of Pegasus, there's a very little naked eye star there. You can see it from dark skies. And that star is 51 Pegasi. Okay, so it's almost exactly the same spectral class as the sun, okay, which means it has roughly the same surface temperature. And so we were looking at it because we were looking for solar systems not unlike ours. So we were looking at stars not unlike ours. And as it turns out, we discovered a planet. Okay, so the first planet we discovered around a sun-like star is called 51 Pegasi b. Okay, it's about half the mass of Jupiter. But the surprising thing about it is it's in a 4.2-day long orbit. Okay, so the Earth is in a 365-day orbit. If you get closer to the sun, the closest star to our own sun, the closest planet to our own sun is Mercury. It's in an 88-day orbit. So this planet is even closer to 51 Pegasi than Mercury is to the sun because it's only in a 4-day long orbit. Okay, so in fact, the orbit of this planet is just 10 stellar radii above the surface of the star. It's extraordinarily close. And so we call this planet a hot Jupiter. It's a Jupiter that's so close to the star, it's just constantly baking in that ultra amount of energy coming off the star. And you can use the things that you and I have talked about to calculate precisely how much energy it's getting using the stellar constant for this star. Now, if the planet's not a hot Jupiter, we do find other planets close in orbits like this. And so you'll also sometimes hear these kinds of worlds called roasters because they're right there up against the star roasting. Okay? Okay. So the interesting thing about this, so this was only the second planet we detected. Okay? And this planet is unlike any planet we've seen in our solar system. It's half the mass of Jupiter and butted right up against the star. Okay, so we have some questions about this, right? The most important is, where did it come from? Because based on everything we think we understand about the formation of planets and everything we think we understand based on systems where we think we see planets forming, we don't have any idea how you could possibly form something like the planet Jupiter, or half the mass of planet Jupiter, that close to a star. There's just no way. If all the gas were down near that, near the star at that point, it would have tremendous influences on it from the wind from the star, from the gravity of the star, from the heat from the star, all kinds of things that should preclude all of that gas collapsing to form a planet. And so the idea has arisen, and this is true of many of the solar systems that we see, is that it probably formed somewhere far away from the parent star, and somehow over time, through either interaction with the protosolar nebula, interaction with small bodies in the solar system, gravitational tugs from other planets, all kinds of things we can imagine, it slowly moved itself in until it got into this very short period orbit just over the surface of its star. Okay, so this was an exotic world when we first discovered it, and it still is an exotic world. It's unlike any world that we've encountered anywhere else. Okay, so this still hasn't helped us. Is the solar system unique or not? And so we just had to keep looking for planets. So the 51 Pegasi b was discovered in the mid to late 90s. And so that was 25-ish years ago. And in the ensuing time, we have done a lot of searching, and we've had a lot of success at finding other planetary systems. So this is a graph kind of like the one that we've seen before. This is from a couple of years ago. The catalog here hasn't been up to date for all the recent discoveries, but it shows the general trends that we see. So on the vertical axis there is the planet mass, okay? And on the lower axis there is the separation from the parent star. Okay, and so what I like about this particular plot, which is why I used it in the talk here, is that it has marked on it the location of all of the planets in our solar system, both in terms of their mass and in terms of their position. Okay, so if you look at where all the planets in our solar system are, and you look at where all the exoplanets we have discovered are, you see that they do not overlap with each other. There are very few exoplanets over there where the planets in our solar system are. The vast majority of exoplanets that we've discovered are in the both high mass, kind of Jupiter and heavier range, and much closer to the parent star than our planets in the solar system are. You'll see the names of these planets here kind of over the groupings. So up there in the upper left, you see they're labeled hot Jupiters. That's where planets like 51 Pegasi b live. There are so-called normal Jupiters, things that are the mass of Jupiter but farther away from the star, not in these kind of really close skimming orbits. They're right over the star. And then there are hot super Earths. So super Earth just means that they're heavier than Earth. But they're hot because they're much closer to their parent star than Earth is. So if you look at the chart here, you'll see lots and lots of those are closer to their parent star than even Mercury is to our sun, okay? So the question is, what's going on? If I were to just take this data the way it looks and look at where our planets are and look at where all the other planets that we've discovered in the galaxy are, we might conclude that the solar system is a bit exotic, that it's unusual in terms of its structure and in terms of the way its planets are organized and in terms of where the planets are, okay? But that would be a foolish conclusion to make at this stage. And the reason is because one of the biggest problems that we have in astronomy, and you see it on full display right here, is there are something called selection effects. What a selection effect is it means when we go out and we look at the universe, certain things are easier to see than others. So the classic example is if you and I go in the backyard with a telescope, okay, and we're cruising around looking at stuff in the night sky, the easiest thing to see are the bright things, okay? So remember we talked about Galileo. Galileo, when he first looked at the night sky, if he looks with his naked eye, he can see a certain number of stars. And so he might conclude that there are only 9,000 stars in the sky based on what he can see with his eye. Well, that's a selection effect. It's completely based on the capability of his eye. Because if you put a telescope on the sky, you discover there are many more fainter stars than the ones you can see with your naked eye. Technology allows you to overcome selection effects and introduces new selection effects of its own. So one of the things we spend a lot of time talking about and thinking about in astronomy are precisely what these selection effects are. And there's big selection effects going on here. Okay, so what is the selection effect that's going on here? The selection effect is that all of the techniques that we use to detect exoplanets are good for heavy planets. So that's why you see things that are way up there by the Jupiter masses and things that happen on short time scales because we're impatient. right? So we are willing to look at something for 1 year, maybe once a couple times every week, maybe a couple times every month for a year, but we have never stared at the same set of stars in the same place in the sky for the length of time it takes Saturn to make its complete orbital transit. Okay, it would take a long time to detect something in Saturn's orbit because you have to observe for 10 or more years in order to get all of the effects. Okay, that's an example of a selection effect. So if I show you a slightly different version, whoops, sorry, stop the slides there. If I show you a slightly different version of this plot, okay, what I've marked here, so again, you see our planets in our solar system marked, but that red line there that you see shows where the boundaries of what Kepler is capable of measuring with its transit method. So anything that's above and to the left of the line, Kepler could detect, and you can see where all of those red stars marked are, okay? Now, in order to make better measurements than Kepler, because Kepler clearly didn't cover the parts of the space here where our planets live, then you have to get better data. There's just no way around it. Okay, well, as it turns out, we are planning for better data. Okay, so there is a forthcoming mission called WFIRST, or it used to be called WFIRST. Some of you may have heard just in the last couple days, this has been named the Roman Space Telescope after Nancy Roman. Nancy Roman was the chair of astronomy at NASA for 20 years in the 1960s and the 1970s. She later worked at Space Telescope and was instrumental in getting Hubble off the ground. Okay, so we've named WFIRST now the Roman Space Telescope after Nancy Roman. So WFIRST will fly in the next kind of 5-ish years, around the middle of the 2020s. And the blue line shows where WFIRST will be sensitive to exoplanets. And as you can see, it covers that huge range of space where Kepler wasn't able to see exoplanets. And that includes lots and lots of the planets in our solar system. The only planet outside there is Mercury. Okay, but Venus and Earth, Mars, all the giant planets are all well within the capability of WFIRST detecting, at least in terms of their orbital and massive parameters. Okay, so the blue dots here are a simulation that shows where WFIRST is expected to observe planets during its mission. Okay, so at this point, so this is a plot showing a lot of the different architectures of worlds that we've seen. So plotted horizontally, the name of the planetary system is over there on the left. I certainly haven't done every planetary system here because there's like 3,000 of them, okay? But then there's a line that shows basically the relative spacing between the planets, how far away it is from its parent star, which is over here where the name is, and then the size of the planet shows its relative size. And so you can see there, if it's the size of Mercury, Earth, Uranus, or Saturn, that's the size it'll be planet. And so what you can see here, looking at this picture, is we have found precious few systems that are anything at all like our own solar system. There either have lots of massive planets much closer to our to their star than our solar system has. Many of them have lots and lots of planets very tightly packed into the inner solar system, which is something we don't see happening in our solar system. There's all kinds of differences that we see here in this data, but we still can't say our home planets are an oddball system because we don't have enough data. If we go back to this WFIRST map, we need to fill in where all those blue areas are and see whether or not any of these systems look like our planetary system or not. And if they don't, then we will have a very strong case for saying, wow, it seems like maybe the planets around the sun are a bit odd. And as we've been discussing this whole quarter, the properties of the planets, which depends on the planet itself and the star, can have profound implications for whether or not their life could be found on that planet. Okay? So the story's far from over at this point. There's still a lot that we need to understand, and we will eventually get there, but we're just never going to understand it unless we get better data. And that's always the way things go in astronomy and science. Okay, So that's all I'm going to say for this part of the lecture. I'll see you for the second half in a little bit, and then we will call it good for our discussion of exoplanets for the quarter. I hope you're all doing well. Make sure you're keeping up on your reading, and let me know if you have any questions, okay? Talk to you all later.